Okay, in this video we're going to be talking about solenoids, and a solenoid is basically a loop of wire, a circular loop of wire. So here we have a loop of wire with current flowing through it. So the current is flowing in one direction around the loop, in this case clockwise. And if we use our right hand rule, so remember the first right hand rule, you grab the wire with your right hand, your thumb pointing in the direction of the current, you find that the magnetic field inside this loop of wire points into the page. No matter where you grab the wire, it's always pointing into the page. And on the opposite side of the wire, on the outside of the loop, the magnetic field is out of the page. So this blue represents the magnetic field. So inside the loop of wire, we've created a region where the magnetic field is uniform. It always points in the same direction. So what we're going to do is turn this loop of wire on its side and wrap it around a hollow core. Like you could think of this in terms of an empty tube. And we wrap the wire around it a bunch of times, and that creates a region where the magnetic field always points in one direction inside the coil and in the opposite direction outside. So we have this uniform magnetic field inside our solenoid. This is useful because we now have a method of creating a constant magnetic field. So how do we determine the magnitude of this magnetic field? Well, we have an equation for the magnetic field in a solenoid, and there's two different forms of the equation. If you look on the formula sheet, it's mu naught times n times I, or mu naught times capital N over L times I. So obviously lowercase n is equal to n divided by L. So what are these constants? Well, n is just the number of loops. So if we went through and counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we would have n for the total number of loops. L is the length of the solenoid. Okay, so again, this length from here to here is the length. So a lowercase n just tells us the number of coils per unit length. So rather than saying there's 1,000 coils and the solenoid is 30 centimeters long, they might just tell us that there is 800 coils per meter. So it's the number of coils per meter already built in. The other thing that's a bit confusing about this formula is this constant, mu0 or mu naught. It's called the permeability of free space, and it's equal to 4 times pi times 10 to the negative 7 Newton meters squared per Tesla squared. So this is a little bit odd because it's 4 times pi times 10. Usually when we write a constant, it's some number times 10. This is 4 times pi. So 4 times pi, if you did that on your calculator, you would find that it's 12.57 times 10 to the negative 7. So why don't we write it as 1.26 times 10 to the negative 6? Well, this constant has to do with the area of the solenoid. So sometimes, not in physics 12, but later on, you might be doing calculations where the pi in this constant will cancel with the pi in the area for the solenoid. So physicists like this version of the constant better because it makes the math simpler when you're canceling the pi for the area. Unfortunately, in physics 12, we don't really do those calculations, so it doesn't really help us. So what you have to remember is when you're putting this into your calculator, it's 4 times pi times 1 times 10 to the negative 7. It's very easy to put this number into your calculator incorrectly. So take a look at some of the example questions that we did from the textbook and make sure that you can get the right answer. If you're not getting the right answer, it might be because you're putting this constant into your calculator incorrectly. So this tells us the magnitude of the magnetic field inside the solenoid. We can determine the direction of the magnetic field, again with our first right-hand rule. Grabbing the wire with our hand, with our thumb pointing in the direction of the current, our fingers tell us the direction of the magnetic field. Okay, and one of the uses for a solenoid, one of the basic uses, is for something called an electromagnet. And an electromagnet is basically a solenoid. So it's a loop of wire around some sort of iron or conductive metal. In this case, we just used a nail. In one of the activities, one of the investigations, you build your own electromagnet. And the useful thing about this is when we close this switch, in other words, turning the current on so that the current is flowing through here, we create a large magnetic field in this iron core, and because its domains will get aligned with the magnetic field that's created, we then have a magnet that we can turn on and off with a switch. And this is useful in a lot of applications. We use solenoids all over the place. There's a solenoid basically in every car. In the starter of your car, there are solenoids in cathode ray tubes. Rather than using electric fields between parallel plates, we use solenoids because we can easily create a magnetic field to deflect that beam of electrons. You can look up on the internet lots of other uses for solenoids. They're quite prevalent in modern society. But the main use here that we're going to be looking at is an electromagnet, which is a magnet that we can then turn on and off with a switch. Okay, so that is solenoids. Try some of the questions in the textbook. Make sure you can calculate the magnitude of the magnetic field. Quite often you're going to be asked to find the magnitude and direction of the magnetic field in a solenoid.